Hello everyone, I am Sharif Alam, and it's my privilege to present our research on an IoT-based autonomous robot for smart farming. This research addresses critical challenges in modern agriculture by combining the power of IoT and AI technologies. To guide you through this presentation, I have organized it into several sections. First, we will know about the authors, then we will begin with an introduction to the problem and solution, followed by a review of existing literature in the field. Next, I will talk you through our methodology and the proposed systems, including its hardware and software components. We will then discuss the results, highlighting the system performance and outcomes before concluding with the takeaways and future work. This project is a collaborative effort among researchers from diverse institutions and fields. The authors of this research are ASM Ahsanul Sarkar Akib, and M. Rezaul Hassan Rishad, Salahin Shourab, MD Shahin Alam Mojumdar, MD Shahriar Rahman, Fatima Jahan Shifa, MD Sharif Alam, it's me, and also MD Abdullah Al Ahsan. Let's move to our next slide. So the global population is growing rapidly, but the agriculture productivity has not kept pace. Traditional farming practices often fail to meet the demand for food due to challenges such as limited resources, climate changes, and inefficiencies in decision making. Our solution lies in precision agriculture, which leverages IoT and AI technologies. IoT connects physical devices like sensors to collect real-time data, while AI processes this data to deliver actionable insights. This combination empowers farmers to make smarter decisions, uh, improving productivity and sustainability. Our literature review explored the current application of IoT, robotics, and AI in agriculture. Studies reveal that ultrasonic navigation systems have improved field operations, while imaging and spectroscopy techniques have enhanced soil monitoring, particularly for nitrogen, phosphorus, and potassium, key indicators of soil health. Digital twins offer real-time virtual models to optimize integrating and crop health. Robotic systems have shown promising results in tasks like seed sowing, pest spraying, and live field monitoring. Um, these advancements ensured us to integrate IoT and machine learning for autonomous farming solutions. Let's move to our next slide. This slide is on the methodology of our paper. Our approach begins with the soil data collection using advanced sensors embedded in the agrobot. These sensors measure nitrogen, phosphorus, potassium levels, and the soil moisture content. The collected data is securely transmitted to a cloud server for storage and analysis. Using machine learning algorithms, we trained models to analyze this data and predict the most suitable crops for each field. Finally, a comparative analysis of these models was performed to determine their accuracy and effectiveness in real-world scenarios. On the right side of the slide, the hardware workflow is shown. The agrobot's hardware integrates several essential components: the APM 2.8 and Arduino Uno microcontrollers manage navigation and robotic functions. Node MCU ESP8266 handles communication with the sensors and the cloud. NPK sensors measure soil nutrients, and a 1500 milliampere LiPo battery ensures consistent power supply. This hardware setup enables the robot to navigate fields autonomously, collect soil samples, and transmit critical data for analysis. So this slide is on our proposed system software components. Let's start. The first part of the software focused on navigation and path planning for the agrobot. We used the APM 2.8 controller and a programmed it with the Mission Planner software. This setup allows the agrobot to navigate autonomously through fields by following predefined GPS waypoints. The APM software also manages advanced features like speed adjustments, loiter points, and a return to home function, ensuring safe and efficient movement. With Mission Planner, we can remotely track the agrobot's progress and adjust its parameters for optimized navigation in real time. Also, a L298 motor driver is used for motor control connected to our APM 2.8. The second part of the software handles data collection and communication with the cloud. We programmed the node MCU ESP8266 to interact with the NPK sensors, which measure nitrogen, phosphorus, potassium levels, and soil moisture in real time. This data is then transmitted securely to a cloud server using HTTPS protocols, ensuring data privacy and integrity. The cloud-based storage allows seamless access to the collected information, which can be further processed and analyzed for decision making. This feature eliminates the need for manual data collecting, saving time and reducing human error. The third part of the software focused on controlling the robotic excavator using precise movements for the excavator's servo motors, enabling it to collect soil samples from multiple locations. The excavator can gather up to 200 grams of soil in a single operation, which is then analyzed for the nutrient content. The control logic ensures smooth and accurate movements of the excavator's arm, making it capable for function effectively even in changing terrain. The component adds significant flexibility and precision to the agrobot's operations. So our final part of the software involves the integration of the machine learning for crop recommendation. We train 6 classification models, including random, forest, XGBoost, and logic regression using a dataset containing soil parameters like nitrogen, phosphorus, potassium, and soil moisture. These models analyze the data collected by the agrobot to predict the most suitable crops for a given field. The XGBoost and the random forest models achieve the highest accuracy, making them reliable for high precision recommendations. The machine learning integration ensures that the agrobot not only collects data but also provides actionable insights to farmers. So let's talk about our results and discussion. Uh, this slide highlights the key achievement of our projects along with an image of our agrobot on the left side. We developed an IoT-based agriculture robot that uses GPS for precision navigation between hubs, how soil data is displayed through the mobile app and website. Additionally, I will cover the machine learning models we used quality and evaluate their accuracy. This advancement showcase how IoT, robotics, and AI are revolutionizing agriculture. So the Mission Planner software played a crucial role in enabling the agrobot's automations navigation. It allowed us to create a waypoint and define precise paths for the robot to follow automatically. Additionally, Mission Planner enables features like speed adjustment, loiter points for specific tasks, and return to home function, ensuring safe and efficient operation through its integration with the APM 2.8 controller. We were able to monitor and control the robot in real time, providing full oversights of its performance and health during operations. The The Mission Planner application was used to create waypoints and monitor the robot cell's status, including battery level, compass calibration, and satellite connectivity. We conducted extensive testing to fine-tune the navigation parameters, optimizing the agrobot's autonomous movements. The robot's performance was evaluated across various field conditions, such as open fields, uneven terrains, and obstacle-rich environments. Based on the data and feedback collected during these tests, we improved the mission plans and navigation algorithm to ensure smoother and more precision movements. The agrobot's NPK sensors delivered accurate and reliable measurements of the soil nutrient levels connected to the NodeMCU ESP8266. This sensor captured real-time data on nitrogen, phosphorus, potassium, and soil moisture. The sensor's stainless steel prop proved durable, resisting corrosion during prolonged field operations. The collected data was transmitted to the cloud where it would be accessed and analyzed. This real-time data measurement ensures that farmers can monitor soil health with precision, leading to informed and timely agricultural practices. Addition to the mobile app, we To ensure accessibility, we developed an mobile application using Reactive. The app displays critical soil parameters, including nitrogen, phosphorus, potassium, and humidity levels, all in real time. Firebase was used as the backend database to store and retrieve data. This user-friendly app enables farmers to monitor soil health directly from their smartphones, providing actionable insights on the go. The initiative design and real-time updates make the app a valuable tool for modern precision agriculture. We also developed a website named IoT Robo.xyz to display soil data visually using PHP and Firebase. Um, oh, The machine learning models trained on the collected data showed promising results. Among the 6 models tested, the random, Foster, and XGBoost classifiers performed the best, achieving an accuracy of 95.16%. The logistics regression achieved 83%, recall of 83.99%, and an F1 score of 82.87%. The KNN classifier had 86.65% precision, 86.05% recall, and an F1 score of 85.2%. The decision tree classifier yielded 93.52% precision, 93.25% recall, and an F1 score of 92.82%. Lastly, the naive bias classifier attained 91.187% recall and an F1 score of 87.58%. These results validate the integration of the machine learning into the agrobot for precise and effective crop prediction. A decision tree and naive Bayes classifier are reliable for the moderately complex tasks with a respectable performance metrics. Our finding highlights the transformative potential of IoT, robotics, and machine learning in agriculture. The autonomous agrobot not only simplifies field operations, but also provided critical data that helps farmers make informed decisions by combining GPS navigation, real-time data collection, and machine learning analysis. We have created a system that enhances efficiency and productivity. Mm, the mobile app and website further ensure accessibility, making this solution practical for farmers. This advancement underscore the importance of integrating cutting-edge technologies into agriculture to address challenges such as food security and sustainability. Let's move to our next slide. The slide is on the conclusion. In conclusion, this research demonstrates the integration of the IoT and AI has brought significant advancement to agriculture by combining smart sensors, IoT communication, and AI-driven decision making. Crop
I think there is a problem of connection on your side. Can you please check? Okay. So, are there any questions about this research? I've got one question about the autonomy time of the prototype that you developed. So, for how much time can it function without recharging? Dr. Sharif Alam, can you hear us?
Yeah, there is some network issues. Could you please ask the question again?
Yeah, I was asking about the autonomy time of this battery-powered prototype. So, for how much time can it function without recharging?
Actually, we have used here lithium-ion battery, and here is a battery of 10,000 milliampere. And we have also this is a rechargeable battery, we know, and we have also the solar system to recharge the battery, and also direct AC system to recharge the battery. And the power capacity, the robot will run by this battery maximum 5 to 6 hours.
Okay, thank you.
Thank you so much.
Any question from the audience? Right. Thank you very much, Dr. Hakim.
Thank you so much.